So we're going to kick things off with a question for you, the audience. How much does the GPU on our MetaQuest devices affect battery life? And let's put some specific numbers in this question. Let's say all of your apps are at 100% utilization of the GPU. You're using the whole thing. And let's say you were able to optimize that down to 80%. So you save 20% of it. How many minutes of battery life are you then going to save your users? If you optimize 20% of it away, what does that equal in minutes of battery life? Let's take some guesses from the audience. Who has any ideas? 5 minutes? Cool. 20, okay. Low and high. One more? 2 hours, okay. So little lower than that. We as Meta, we actually are going to refrain from giving a very hard exact answer just because it's so dependent on so many different scenarios. But what we will say is that those first two answers were somewhere within the right ballpark. Let's say somewhere in that ballpark of 5-10 minutes. And it depends on so many different unique characteristics to your app, to whatever else is running on the app at a given time, like hand tracking, things like that. But we started today's talk off with that example to show that performance cannot just be an afterthought. See, everyone knows that it matters for those developers just pushing the visual fidelity, graphics, trying to get maybe more than 1,000 draw calls per frame, or pushing like PBR materials. And performance matters so much for those devs because you're just simply not going to be able to achieve a visual style like that without optimizing every last bit. But even if that's not you, and it's probably not a lot of you, perf matters for so many other reasons. Battery life is a pretty salient example of that, as we just said. But there's also loading time. There's the difference between a 10-second and a 20-second load. That is an optimization problem. Then there's FPS, 90 FPS with pretty much no frame drops. That versus a choppy, stale frame-heavy 72 hertz is going to make a world of difference for your users' comfort. So that's why that's why we care so much about performance. It's why we spend a lot of time trying to optimize your apps. It's why we're devoting a talk today to it. And that's what I spend a lot of my time doing. I'm Neil. I'm a tech lead at Meta. And the main focus of me and some of the teams around me, some of the Meta folks in the audience, as well as a lot of you devs yourselves, are trying to squeeze a little bit more of the performance out of these MetaQuest apps. So we have a pretty exciting agenda ahead today on that note. First, which is really the big update that we're sharing today, is going to be the big rock that we feel we've been able to move, which is solving a lot of the concerns and problems and pain points that your apps have had to deal with shader compilation. And this is not a new problem. It's existed on pretty much every 3D graphics platform ever, consoles, PC, and Quest is no exception. A lot of you have been mentioning these pain points for a while, and we're really happy to share the updates here. Then we're going to go through what is often the bulk of a Connect session like this, which is just those multiple CPU and GPU wins that stack really nicely, one on top of another, that just make your frame budget a lot smaller for the same amount of work. And that's pretty nice because even if you don't feel like you're bottlenecked by like the CPU or GPU, you could still get that free battery life win. So we think what we're going to share there is pretty much a must integrate for every one of your apps. Then we're going to almost switch gears and talk about a slightly unconventional topic, which is preventing regressions. But the reason that matters is that there's no point in doing all of this work to optimize if we're just going to go backwards on your latest app update. Preventing that regression on every one of your app updates is as important as finding new wins itself. And finally, at the end, we're going to do a pretty fun deep dive on one particular performance tool named Perfetto. If you want a broad-based view of a lot of tools, you can look at the tool session that's happening, I think, 2 hours in this room. But for now, we're going to actually do a deep dive, which is going to be a case study on one specific performance bug that we think could hardly have been solved, maybe not solved at all, or at least taken much longer without a tool of Perfetto's caliber. And last but not least, there's going to be plenty of time at the end for Q&A. So stay tuned, and please hold your questions, but probably 8 to 10 minutes there. So let's start with shader compilation. So what makes shader compilation such a hard problem and so bad for your users, for you developers? Why is it a problem that is worth solving in the first place? Let's take a quick poll from the audience. Does anyone want to raise their hand and say some of the reasons why shader compilation has caused you some pain?
It makes your app freeze sometimes if they're uncompiled. So.
That's a great answer. And since not everyone's mic'd up, I'll just repeat these. This gentleman said it makes your app freeze if they're not compiled, and that's a great point. These are stale frames. You'll be like, the user will look somewhere else. They'll see a new object for the first time. That means a new material, a new shader, a new pipeline state that needs to be compiled. Boom, you're met with multiple frame drops. Could be a few frame drops, could be a few seconds worth of frame drops, anywhere in between. So it's a great answer. Anyone else have a new one? Yeah, let's go. These two, yeah. You first.
Yeah. I mean, if you're a gamer and you're playing games and you run a game and you're just compiling shader.
That's a great answer. So what you just mentioned is this, Unreal Engine calls it performing one-time optimization. We've seen a lot of MetaQuest games like Resident Evil 4, pretty much every Unreal app out there is, they meet their users with this performing one-time optimization initial loading screen. And what it's doing there is it's pre-warming all of these shaders that the user might eventually need to encounter. So for now, we'll stick with these two answers, but you guys just covered, pretty much a lot of the pain points. So as a quick primer for everyone else in the audience, maybe some people who aren't aware of these struggles, the reason why this is a problem is that graphics drivers, namely graphics APIs like Vulkan, which is the dominant API on Quest to use, they compile what's known as pipeline state objects for your apps to even be able to render. All that really means is that the way your shaders go from whatever you write in maybe a game engine, you're writing them in something like HLSL, the way those go down to actual GPU programs for your app to run to then execute the look and feel of your app, these are compiled into these many combinations of these pipeline state objects. And all you really need to know is that there are a bunch of them. So whenever there's a lot of them, your app pretty much has to get clever in how to compile these. If you don't compile them, your app's not going to be able to render. These are the GPU programs that are actually running for your app. So you have to compile them. And if compiling them takes a while, apps sort of have to resort to these weird tricks in saving this compilation cost. So today, apps sort of do one of two things, which is what both audience answers just alluded to. The first answer that you developers have to pick is long loading times. It's exactly what was just said, the performing one-time optimization step. The reason this is still a pretty good thing that game engines like Unreal and even Unity and Unity 6, they've shipped these graphic state collection APIs to allow developers to do this. The reason game engines do this is that at least this means that once you've done this long initial loading step, you are pretty much warmed. You have pre-warmed the shaders. Now your users can get a stutter-free experience. They can play the app, and it's going to feel good. But you do subject your users to that very long load time. And it's not just once. It's once, and then if we have a graphics driver update, which happens pretty frequently, you subject them to it again 1 or 2 months later when we do that. So that's not a great solution. But even worse is the second one, which is what the first answer in the audience said. That if you don't do that pre-warming step, you are going to be subjecting your users to a ton of frequent hitches. Every time they see that new object for the first time, the new material, boom, multiple frame drops. So the conclusion here is that both options are honestly pretty bad. And I think the worst part about option one, even though it's a pretty good option for at least alleviating that user discomfort, it requires a decent amount of work for you developers. Either you need to do some work maybe in engines like Unity to integrate these pre-warming APIs, or in engines like Unreal Engine, you often have to do this 10-hour QA run to even grab this list of all PSO objects to compile. This is not a free process. So we, Meta, decided to take direct aim at the weaknesses of both these today's solutions. We wanted to prevent either long load times, any of these frame drops, and we also wanted to prevent you developers from having to do a lot of work around shader compile to begin with. So it led us to think, could we do anything better and solve some of these pain points? And it turns out that we could. And it was based on this idea that if all of you in the audience are playing the exact same game, let's say some app like Batman Arkham Shadow, even though you're all going to be subject to the same shader compile operations, the output is somewhat similar. You're essentially compiling the same data. So it's not really a unique operation per user. And that means that when we went to the drawing board, we realized that we could design a system that actually accumulated these caches from individual users and then took those, processed them in the back end, and then distributed them to all future users, the bulk of your entire user base. So here's a few details for how the system works in practice. the day that a new binary, a new build, gets uploaded to, not to the MetaQuest store, but to any release channel. This can be in a beta, alpha, or the live store release channel. The backend cache that we maintain is going to start fresh. It's going to be blank because you just created that binary. And from that point on, anytime any user starts playing your app, cache data is going to be generated just by them playing. They don't need to do anything special. This is what already happens today. That's why you have those long loads or those frame drops. Cache data is going to be generated. That is going to be uploaded to our backend, and then we're going to process it. And every time this happens, we're going to merge these together until the backend has a pretty good cache representation. This is called a warm cache, a cache that's ready to really give all of your users to alleviate all these problems. And ultimately, the goal of all of this is to have this cache converge as fast as possible, because once the cache is converged, once it's called warm, your users will not be subject to any of these problems anymore. So here is a visual example that really demonstrates what this cache convergence is going to look like. And it's a pure hypothetical. This was not taken with an example app, but we still think it illustrates exactly how the system works. So every data point is a new user. Your user number one, maybe they grab your app, pretty short play session, 10 minutes. Maybe they play the menu scene, level 1, level 2, and then they log off after 10 minutes. There is still some cache data there, because that first time launch had to pre-warm some of the shaders. Then your user number 2 comes along, and they have a much longer play session, only 30 minutes in this case, but maybe they played a bunch of different levels. And now the union of user 1 and 2 might be 60% of all the cache data that your app has. And all you really need to understand with this graph is that it starts to converge. It grows over time. It gets closer and closer to a warm cache. And once you have a warm cache, your users don't pay the cost of shader compile anymore. And this is, it really falls off asymptotically. It may take days to get to like 100%, but maybe you're going to be at 99.8% for, after like day 1. Whatever the numbers will be, it's going to be app specific, so you're going to have to try it out. Maybe the best part about this, we think, is that these first few users can actually be you devs in a studio play session. Because the elephant in the room here is that those first few users are still getting the negatives of shader compile. They're just they're really compiling the shaders, and then everyone else is benefiting. But that can be you. If you make a new beta build on Monday, and you're releasing Friday of every week, on Tuesday, Wednesday, Thursday, when you do your in-studio play sessions, by the end of that process, this cache is probably warm, and you're probably in a good state. So overall, the homework is that this is actually an unreleased feature. You will all be the first to know the day it releases, but we're still doing those finishing touches on it to get it out there. We think this is going to be a must integrate for pretty much all of your apps. And when we release it, please check it out. It's going to land in a new OS version. And maybe that's a good piece of news, because this doesn't require you to do one of those heavy upgrades to Unity 6.3 or something of the like. You'll be able to get it just by making minimal changes to your app by a lot of the nitty-gritty details that we've landed in our Horizon OS itself. So next, we're going to discuss what is sort of often the bulk of a Connect session like this, just those multiple perf-enhancing features that really just stack up one on top of another. We're going to start with the CPU. We're going to share a few CPU wins here. So it's probably obvious why we're trying to give you more CPU perf, but it just bears repeating a little bit why we think CPU performance is something worth optimizing in the first place. And it's ultimately that it's where that core business logic, game logic of a lot of your apps go. Sometimes I like to say that if rendering and GPU performance is about the look of your apps, often CPU performance might be about the feel. That's where physics simulation goes and similar types of work. So CPU performance is pretty important. Often, I'm sure a lot of you devs have been in a scenario where you're at like 8 concurrent players, some number like that, and you're trying to up that to 9, 10, 11, 12, and the bottleneck you see is maybe Unity main thread or Unreal Engine game thread, just being that bottleneck and preventing that number from going even higher. So we decided to apply an industry standard technique known as link time optimization, which is, it's not VR, Unity, engine specific at all. It's something that can apply in arbitrary binaries at the compiler level, and it really just gives you free performance with very few trade-offs. Some of the only trade-offs are at compile time, and the good thing with an engine like Unity is that you don't pay the compile time cost, because Unity is building their engine, and they're distributing the binaries to you, and you just use the engine out of the box. So this feature, Unity Runtime LTO, it has landed in Unity 6.2 because we gave Unity some PRs, and they were gracious enough to work with us to get it right. it delivers a 6% CPU speedup of Unity runtime code. This is a good time to mention that not all of the CPU cost in your Unity apps is Unity runtime code. There's usually a pretty even split between this runtime code, that back-end engine code that forms the bulk of what Unity does, and then the C# code, which is a lot of what you devs are writing. So in this example, if Unity runtime code was 50% of the CPU cost of your app, we just gave you roughly a 3% win. And the size of the win is going to be content dependent. All you got to do is jump to Unity 6.2 and enable it. But I just want to call out that there are very few free CPU wins of this variety. There's very few free hardware wins coming. Even industry-wide, if you've paid attention to some of these like Moore's Law type slowdowns. So whenever we can get a software side big win like this, it's pretty much a must integrate for all of you. Then we're going to discuss something which is also a CPU win, but not so much for sustaining FPS, but rather for improving load time. We're excited to share the Boost API. And as the name suggests, this is an API that allows you to boost CPU frequency during certain short-lived durations. We think it's essentially really just a loading time speedup. And the reason is app loading, this could be first app launch, or it could also be scene load, where you've launched your app minutes ago, but maybe you're doing a scene transition from level 1 to level 2. This is usually CPU bound. A lot of people assume it's also I/O bound, which means moving data from your file storage into memory, but it's predominantly CPU bound. And that's why giving your CPU a boost during this sequence is one of the easiest ways to pretty much linearly improve the loading time of your apps. So we're really happy to say that this Boost API is a 15 and up to 15% speed up to these in-app loading scenarios. And it's dead simple to use. It really just functions as a start boost, end boost. It's all you got to do. It works really similarly just as another enum in today's existing OpenXR performance mode. So if you're already doing this with Unity, you have those sustained low, sustained high type performance modes. This is just another one named Boost. There are two disclaimers to point out, though. The first is that this API is rate limited to only being enabled 20% of the time. And that's because if we could give you this boost 100% of the time, we would, but we would have done it already. That means you could get it at all times. The good news is loading is not something that is going to need to happen all the time. 20% is actually probably fairly generous, because if you're subjecting your users to having to sit and twiddle their thumbs waiting for loads to happen more than 20% of the time, you probably got bigger problems anyways. So we think that rate limit's not going to be an issue, but definitely don't try and call that for more than 20%. So more than like 24 seconds every 120 seconds is an example. The second thing to call out is that it's a non-guaranteed boost. That means there might be scenarios where you try and get the boost, and then you just don't get granted it. The good news is in that scenario, you're not going to get bad performance. You're just going to get your base level, whether that's CPU level 4, CPU level 5, whatever your base case performance was, you'll still get that. But you may not get this max frequency boost in those scenarios. The reason it's not guaranteed is that sometimes there are these unavoidable thermal constraints that that would make it unsafe to grant the boost. So we're doing this for a pretty good reason. The way that affects your design constraints, though, is you don't want to assume you're always getting the boost. So what you definitely don't want to do is be in like a 63 FPS scenario and say, oh, I'm going to boost so that I can get to 72, 15% higher. That would be bad, because then in the scenarios where the boost isn't granted, you're going to be left with pretty poor perf. But the loading scenario is a perfect fit for this, because it's OK to have users get like a 13-second load instead of an 11-second load. They're not going to feel the discomfort of frame drops. So the takeaway is just use this judiciously. Now we're going to talk about the GPU a little bit. And we have a pretty fun improvement to share here, which is that there's this new feature known as tile properties. And the details here are really just abstracted away from the developer. You really don't need to know too much about it. I'll give a quick preview, but the idea is essentially that our MetaQuest devices, using these Qualcomm Adreno GPUs, use something known as a tiled render. And all that means is that your render pass is divided into a series of tiles. And if Unity passes this tile data to our system, to our OpenXR runtime, our compositor, we can make slightly more precise recommendations, either for dynamic resolution, we can choose a slightly more optimal resolution, or for fixed foveated rendering. At the same visual quality, we can actually squeeze a little bit more performance out of it. We can do FFR slightly more optimally. So all you need to do here is actually upgrade to Unity 6.3, which has not come out yet, but this feature is landing there. So it's just like LTO in terms of being a purely free win. Definitely grab it when we're there. And then there's dynamic resolution, which we just alluded to. So this one's interesting because it's not a new feature at all. We've presented it at past Connects. Certain people have been highly recommending it, like the Breachers developers, Triangle Factory. They adopted it a few months ago and saw some really good visuals as a result. As a quick primer to anyone who doesn't know about this feature, it uses any spare GPU headroom that exists in the device to just up the visual quality of apps. So it sounds like a good win. It's adaptive, which means that if there's not any spare headroom in a certain scenario, it's not going to bump up. But if there is, it's going to bump up a bunch. But a question that we've got from some of you devs is, what's the point? What's the real end goal of doing all of that? Does visual quality really even matter? Like, sure, dynamic resolution it's providing an undeniable visual quality win to apps, but do your users really care? And we think that's a fair question. Some of you devs are so interested in upping the graphics that you're going to adopt features like this anyways. But to the rest of you, we, Meta, need to probably do a good job at trying to really demonstrate the ROI of certain types of these features. So we went to the drawing board, and we realized that maybe we could do something clever. We might be able to ship an experiment with one of our apps where we were able to deliver a resolution boost to them and see, answer that question once and for all. Did that show any time spent increase? Did that show any daily active user increase? So we partnered with another Axiom, creators of Gorilla Tag, to ship that exact experiment in our OS a few months ago. And the results were pretty stunning. We found that visual quality did indeed affect Gorilla Tag's usage, because in the 50% of all users in our experiment who had higher resolution, in this case, they had 60% more pixels, that cohort of users had 1.81% more daily active users. So this sent just this unassailable statistical conclusion that upping the visual fidelity of Gorilla Tag did actually increase the user time spent, the daily active users of Gorilla Tag. And the reason we were able to up the visual fidelity, the number of pixels by 60%, is that they actually had a lot of GPU headroom. And that's the good thing about using a feature like dynamic resolution, is that it's only going to up based on whatever the headroom that you have is. So it's pretty safe. If you don't have much headroom, great, it's not going to do much. So maybe the takeaway from this slide is that if you don't adopt features like dynamic resolution, you might just be leaving daily active users and time spent on the table. So next, we're going to talk about that interesting topic, which is preventing performance regressions. And it's not always discussed in Connect talks like this. The focus is always, what were those new wins we landed? And those are great. You just heard about a bunch of those for 15 minutes. But what's the point of doing all of that if you're just going to squander 5% maybe GPU perf in your latest app update? There's no point. So we've really tried to make that regression prevention story a little bit better. And we're happy to share a couple things here. So we think there's roughly 2 good paths to ensure that your apps are trying to guard your app's update today, from regressing. And this is not just regressing performance, although performance is pretty important, but this would be things like regressing crash rate. So path number 1 is measuring performance in automation. And quick show of hands, who out here does this, which is has end-to-end automation tests that run on Quest 3s, Quest 2s, and are going to scripted run through your apps? Cool, so we have a few hands, but not that many, and honestly, I can't blame you. It's a pretty painstaking process. It requires you to do things like set up a rack of multiple different Meta Quest 2s, Quest 3s, all being able to run new versions of your build. It's a lot, and this is something that we can't expect every developer to devote that much time to it. So we have, one of the other hard parts about this is that even if you are able to set up that infrastructure, you then need to do a lot of work to grab the right metrics. You need to create these Python scripts to grab CPU counters, GPU, frame time, memory usage. And a lot of this is like pretty painstaking. We don't want to subject you developers to this. So we feel like we've made it a little bit easier to do that via some benchmarking APIs. Now the second path doesn't rely on automation at all. There's this new phase releases feature, which we shipped a few months ago, and we're going to try and make the claim that even if you don't have these automated tests, as long as you can roll your app update out in phases, that is the single best way to verify that that new version is not going to cause these types of updates, regressions. So let's go through some of these in detail. First, we're discussing, as we said earlier, we are introducing these new perf benchmarking APIs. And these function pretty straightforwardly that you really just need to turn your automation tests into a sequence of start workload, end workload calls. And we're going to take a look at this. This is a Unity test sample that we were able to bootstrap with these types of APIs. So we're starting it here. It's just an on-Rails motion, similar maybe to what some of your automation tests run. It's hard to see here, but it says starting workload bathtub. So they called start workload. And then in a few seconds, we're going to see ending workload bathtub right around now. And then now starting workload carpet hall. And now ending workload carpet hall, starting another workload, ending another workload. And what we're doing here, it's not that complex. We think it's something that a lot of you apps could do. But by doing this, we are demarcating certain important segments of your app. And then we're going to be able to measure all of the performance in between those segments really reliably. So once you've called these APIs, and that's really all you need to do, we're going to generate these CSV files where between these segments, every second we're pulling all of the metrics that we think you would need. GPU time, memory consumption, FPS, et cetera, really similar to the OVR metrics tool metrics that a lot of you might rely on today. So the takeaway here is that you can probably get away with not even writing these types of Python scripts. You would just need to call the start workload, end workload, and then in between there, you're going to be able to get these end-to-end CSV files, which then you can compare the output of those to see, oh, wow, the CSV file says that my app time spiked from 4 milliseconds to 6 milliseconds. That's a regression. Now, even beyond automation testing, because we agree there is a certain amount of investment that every one of you developers have to do in automation, even if you're not able to do that, we think that there are probably better ways for you to guard your app update than what some of you might be doing today. And that brings us to this phased releases feature. So the reason why this phased releases feature matters is it sort of goes back to why we had to do that Gorilla Tag experiment in this A/B experiment, as we said a few minutes ago. And the idea there is that you only get predictive power if you change one variable at a time. So I'll give a hypothetical example. Let's say you ship your latest app update on September 20th. But on September 21st, maybe we ship a new version of our MetaQuest Horizon OS. And these things can line up in similar dates pretty frequently. I'm sure a lot of you have seen confusion on the days that we ship out new OS versions. And let's say on September 22nd, a lot of your users start using a certain part of your app a little bit more. Maybe a new golf course in Golf Plus. And maybe that course happens to be a little lower FPS. So the question I'll pose to the audience is that if FPS starts to degrade around September 21st in that scenario, what's it the fault of? Is it the fault of no one because maybe that new map in Golf Plus just happened to be lower performance, but it's not like a performance loss happened. It's just the users happen to be spending more time in a different part of the app. Is it the fault of our OS, or is it the fault of your app, and then that's something you would want to change yourself? And the reason why you would need to release your app in phases is that you're only isolating this one variable, which is your app version change. Because the 50% of all your users that would then be in the old version, and then you have another 50% in the new version, both cohorts have every other detail really the same. They're either going to be in, let's say, the V78 version of the OS or the V79 version of the OS. Those other variables will be held constant. Or on September 20th, they'll be in the old map. On September 23rd, they'll be in the new map. And then the conclusion here is that without using a feature like this, it's just so hard to attribute a perf drop or anything. It could even be a crash rate spike. This feature is really important even beyond just measuring performance. It's so hard to attribute that to your app update. So we think that this is just a must integrate. And the last thing we'll leave you with in this feature is that sometimes developers have said that this feature is a little bit harder to use for things like new content drops. You don't want to hide a big brand new content drop behind like a 50% gating. You want to give it to all your users. And we hear you loud and clear. So what we might recommend is you don't need to use this feature in every one of your app updates. But some of your app updates might be that big Unity 6 upgrade from Unity 2022. There's no new feature there, but you still, it's the type of thing that keeps you up at night, knowing, did that big Unity 6 migration, did it break anything? Hey, my automation tests are green, but maybe it spiked load time. Maybe it spiked memory consumption in world number 10. And it's so hard to scientifically attribute that, but We feel that with the feature like phase releases, you can. So the takeaway is, even if you can't use this feature for every single one of your app updates, you don't need to, but just try and use it for those big ones, the hammers that would otherwise really jeopardize your app stability. And finally, we get to a pretty fun part, which is a tools deep dive on Perfetto. So as I said earlier, if you want a broad-based discussion of tools, you can check out David and Mike's talk in this room in a couple hours. And that's why we're instead going to do a deep dive onto one specific tool in particular. And the nice thing about this deep dive is that it's going to be a case study. And in this case study, we're going to go through a performance bug that we actually had to integrate. So you know that we're not just giving you a tool's feature set. We're telling you that without a tool of this caliber, we would not have been able to solve this type of performance bug in the same way. So hopefully from this, you'll learn a little bit more about this tool, and maybe you'll give it a try. First things first, what is Perfetto? So show of hands, who knows what Perfetto is? It's pretty good, honestly, like 70% of the room. I'm sure, David, it's higher than we might have thought. That's good. At least awareness is getting out there. Now, slightly harder question, who uses it regularly? Okay, I'm actually impressed. There's about 4 or 5 power users, but yes, the number is not that high. Part of what we want to do the next few minutes is maybe bridge that gap by showing you that there really are these essential capabilities in a tool like this. So what it is this Android system-wide profiling tool. It's actually very analogous to what Unity's CPU profiler has, as well as what Unreal's Insights profiler has, but Perfetto operates entirely at the system level. It doesn't operate inside a game engine, and that means you get a lot of these system events, but also fused with these app markers with the Perfetto track event API. Those app markers are basically exactly what you would see inside Unreal Insights or the Unity profiler. So you'll get a lot of these profilers as long as you have a development build of your app. So first things first, why Perfetto? What is this feature set that I'm trying to even pitch you all on that you can't really get in another tool? I'm going to claim that the combination of what I'm about to share, it's a combo that you're not going to get anywhere else. You may get 1 or 2 of them in isolation, but not the overall combo. So let's start with the simple stuff, just answering, where are you bounded by? And this is something that I'm sure a lot of you have seen before. You're at like 60 FPS, not 72. Or better yet, you're at like 70, not 90, because 90 hertz is really high quality. So you're at 70 hertz instead of 90. What's the problem? And I'm actually going to make the claim that Perfetto is the single best tool for that. There are other good tools too. OVR Metrics tool is an incredible one, and I'm sure a lot of you use it, and you should keep using it. But what's nice about Perfetto is that it allows you to view frame by frame different details because you have this timeline view. Other tools like OVR Metrics tool have to aggregate everything all into like a few statistics, and that makes sense because of the way it's presented. A lot of these are streamed in once every second a new metric comes in. But with Perfetto, you can look at individual frames one by one, which is pretty cool. So first things first, it may be the best tool to just see what you're bounded by. Then, which is truly something you only get in Perfetto, you get this full view of every thread running in the CPU. And this is something where I'm also going to be totally honest. Not all of you need this. So if that doesn't interest you, you don't always need to look at this. It could even just be confusing. Because a lot of what is running in the CPU system-wide has nothing to do with your apps. It might be these algorithms that we need to run on our Meta Horizon OS software end to even power hand tracking, power inside-out tracking. But what's nice is that having that full view is important because your apps, they don't exist in isolation. They exist as a combination. Sometimes there are interactions between your apps and some system threads. And as a sneak peek, that's what we're going to see in a few minutes. It's really good for this needle in a haystack view. And the idea there is that, what if your app is at 68 out of 72 FPS? Often that means that you only need to look at these like 4 problematic frames. You don't need to look at everything because those other 68 frames might be good. It might just be these like asynchronous jobs that are just like popping up from time to time, and you want to narrow down those. So Perfetto is really good at allowing you to zero in the problematic frames. And finally, maybe the most underrated piece is these CPU and GPU events can get unified in one shared timeline. A lot of other tools, they're CPU-centric, which is fine, but sometimes it's nice to see how the CPU to GPU handoff occurs. So just a couple quick slides and a little bit about Perfetto feature set before we go through this deep dive. There's a CPU scheduling view at the top. It's maybe the most important part. It just allows you to see every CPU core that exists in the device, what's running on it. You'll see here that the Unity app that we're profiling, it's only running in the bottom 3 cores, and that's because in the MetaQuest 3 and 3S, that is just our core split. Your apps get the bottom 3. Our system has reserved these top 3. Then, though, there's this pretty cool per process breakdown. And this is nice because if you just look at the CPU view at the top, you're really kind of looking at this clusters that are unlabeled of cost, but you want to know the why. Like, so what's actually going on in this cost? So you can open the per process view, which is great, and you're immediately greeted with a lot of cool identifying info. This is similar to the stuff that I was saying. Unity tags a lot of these events themselves. Unreal tags them. If you have a development build, which I don't even have right now, but if you have one, you'll be able to see a bunch of events. The nice thing you'll also see is frame indices. So 4299, that's the given frame we're on, and that's so important because you get this I'll call it life of a VR frame profiling. You can start with, this is the very top of when a frame starts, frame index 4299. Then you see it's in orange there. It's kind of hard to make out, but 4299, it's doing input processing for frame 4299. Then it's going to do rendering for that frame, and finally it's going to do GPU work for that frame. So this cohesive CPU-GPU view is something you don't really get elsewhere. Now for the fun stuff, the case study. So we had this performance bug where FPS, it dropped sharply from 72 down to 67. And the main question was why? And as we said earlier, we feel that Perfetto was one of the only tools that could diagnose this to this level of rigor. So the first hero feature is just scan that timeline view and find the problematic frames. And we did that, and we were able to see that with enough of the scanning, there were a few anomalous frames. Some were not like the others. This is one such frame. And you found that there's this one function call, XR get device sample rate, which is an OpenXR function. It took a whopping 3.3 milliseconds to execute. That's 30% of your overall main thread frame time if you're at 90 hertz, or like 25% if you're at 72. And that's just outrageous. But the other thing is that other frames don't have this. Only some frames have this cost. Most don't. And that's why we were at 67 FPS. We weren't at 10 FPS. Most frames weren't subject to this, but these few kept popping up with that extra work. So then other tools, I think, could maybe pinpoint that one specific function was slow, like here, XR get device sample rate. But Perfetto's benefits really start from here, which is that they can help you answer the why. Why is that specific function slow? And this gets us into Perfetto's visualization of what are known as Linux thread states. We don't need to know too much about that. All you need to know is that threads can be running, they can be sleeping, and they can be a few other states. And here, it might be hard to make out, but you can see that this thread is sleeping during the entire duration of this 3.3 milliseconds, which is kind of an oxymoron. This is when your main thread should be running. It should be fed with work. It should be doing a lot of important stuff. Physics simulation, C# behavior update, et cetera. But it's actually sleeping, and that's problem number one. But it doesn't end there, because Perfetto, it actually allows you to see the why behind the sleep. And that's the part you're just not going to get elsewhere. You're not going to get in any other tool. So the why behind the sleep is really important, because there's many reasons a thread could be sleeping. You could literally call sleep 5 milliseconds, right? You could be waiting in a semaphore that some other thread then has to signal you on. And in this case, it was the latter. And Perfetto allowed us to see that, because we could click on the CPU track up top from above at the end of where this slumber has concluded. And if you look at the bottom right, we could see this wake up. And the wake up means that that thread, the Unity main thread, when it wakes up from the sleep, it's woken up by another thread. And if we then trace that thread, we find that that thread was woken up by the main thread. So we see that this circular dependency was going on, where the main thread was essentially waiting in another thread for to do some CPU computation. And that was the entire reason for the slowdown, because that system thread, it was actually not a thread in the application. It was a system thread. That was taking forever. So an overall summary, if that was a mouthful, is that the main thread was doing what's known as a blocking call. These are definitely an anti-pattern in CPU programming, not something you want too much. It was doing a blocking call, waiting in system work to complete. The system thread took a while to be scheduled, 3.3 milliseconds, and only once it was scheduled could it even finish and cede control back. And that's just an instant frame drop, because the main thread was stalled for 3.3 milliseconds. Now, we think that Perfetto really uniquely enabled almost all of this. It gave that initial diagnosis, which sure, you can kind of get in other profilers, but if you use something like OVR Metrics tool, maybe you wouldn't know that only a few frames are bad. because most frames actually were good. It allowed you to visualize system threads, which was really important because that's where the problem was. And then it allowed that visualization of dependencies to see, oh yeah, why is Unity main waiting in the system thread work to complete? It's just this type of perf investigation that maybe never gets solved without a tool of this caliber. So what we'll say is that we understand it's a tool that sometimes has a little bit of friction to use, and we get it. Not all of you need to be using it, but maybe some of you might want to give it a little bit more of a try. So that pretty much gets us near the end here. To recap, we've shared a bunch of stuff here. The big update was that we've really been able to, we feel, move some rocks behind that major bounding factor of what shader compile, the amount of pain that's causing a lot of your apps today, whether that be long loads, frame drops if you don't subject your users to those long loads, or worst of all, a lot of dev work to even do that pre-warming process. Then we were able to share a bunch of these CPU and GPU wins, which we think all of you devs just need to be stacking them up one after another. They work pretty nicely in tandem with one another. Definitely get in those newest versions of Unity 6.2, 6.3. Even if you're on Unreal, you can use the Boost API and a few others. And those are pretty much must integrate features. Then we did a little bit about regression prevention. Introduced these new APIs and shared a little bit about phased releases. And finally, we did a Perfetto deep dive and hope that we might just have convinced you to add this to your performance toolkit. So thank you. That wraps it up. And now we have about 5 minutes left for Q&A, so please come up.
Great stuff, Neil. On the Perfetto stuff, I had a couple questions. One, when you're running Perfetto, does it have any negative impact on performance while it's running and collecting data?
Thanks, Ryan. It's a great question. It does have a negative effect in that it all depends on the number of markers that are being submitted. It's funny. This is actually something that me and David were talking about a couple days ago. Unity and Unreal tend to be very, let's call it chatty. They're inserting just a bunch of these markers, like thousands per frame. If you're doing that, you are going to see like a frame rate degradation. You might go from 72 to like 50 FPS. But if you have a release build of your app, then you can still get a lot of the benefits. Because I was profiling on a release build. You're still getting those like frame indices, these extra runtime markers. So I would say there are modes that can have an almost negligible perf drop, like what I profiled with. But if you really layer on the Unity markers, I still think it's beneficial. And I'll tell you why. Even if sure, your app is going to be whatever, like 40 FPS, and that's not good because usually Golf Plus is a lot higher. It allows you to still see that certain things are still more expensive than the rest. So it still has value.
Cool, it's relative. That makes sense. And then the other question I had is the example that you shared where you found out there was like this system call that caused the frame drop. In that example, if we like see something similar where there's this like system call that's 3 milliseconds instead of 0.3 or whatever.
Yep.
Is there anything we can actually do about that other than know that once in a while this thing gets stuck? Or was there something happening on like the client that we have control over that was causing this to get blocked?
It's another great point, and I think it's both. So number one, these are certain anti-patterns that we as Meta, we need to not be introducing them through our OpenXR stack. But there was actually a C# line in our Unity Meta XR Core SDK that was kicking off this work. So whenever we find things like this, maybe we'd give you a code pointer. Newest version of the Meta XR Core SDK will not be doing that. So in this case, it was something your app could probably work around. But I agree that like for specific cases like that, we probably should just design our software so that it never hits you to begin with.
Yeah, of course. I mean, yeah, if you could design perfect software, that would be great. But if we do see stuff like that, should we just sort of report it to you guys, let you know that we found something, send you the Perfetto file or whatever to help?
That would be amazing. Any and all traces, we'd love to take a look.
Cool. Awesome. Thanks.
Thanks, Ryan. Next. And sorry, I probably went a little fast, so we only have like a minute and a half left, but maybe we can get both of these. Yeah.
Okay.
You can go long for a little bit.
Okay, thanks, Thomas.
All right. Well, thank you again for your talk. I have a story some might be able to relate to. I'm an artist who was forced into the position of doing performance traces on games just because that's the nature of Quest. And I found RenderDoc's metaphor should be very useful in the visual frame capture, how easy it is to break down the parts of the frame, understand where those material costs are coming from. Does Perfetto have a similar visual debugging system, or would you recommend anywhere for starting to learn this sort of pipeline?
Yeah. First of all, it's a great point overall. Like my and David's teams, we both are building, both the RenderDoc metaphoric, these Perfetto integrations, and the overall tool story. So kind of what I alluded to earlier, David's going to talk about RenderDoc and some of those other GPU tools as well. My answer would be that, so it sounds like you're saying that RenderDoc was really useful because you don't just get that top-level frame time view that, sure, it's like 13 milliseconds, but then you get a breakdown. You see that 1 millisecond is this draw call, right? And then you get to dive deep in that saying, why does it take 1 millisecond? Oh, it's these textures, right? And is that sort of what you're getting at there?
Exactly, yeah.
Perfect. So the Perfetto analog is essentially that you get the overall frame time of Perfetto, and then you need to rely on these markers to then start digging deep. So I think the answer is that it's either up to the game engines, Unity, Unreal, or to you to add these markers. Because Unity, for example, they've exposed these C# markers. I think it's called profiler, begin, end. You can insert Perfetto markers for your own app. So if you found that physics update is particularly bad, insert some markers in your end, and then you won't just be met with this like 10 millisecond blob anymore. You'll be able to break that down like, oh yeah, 1 millisecond for this game object or actor in Unreal, things like that.
Okay, thanks so much. Appreciate that.
Thanks.
What's up, Neil? Sick work on the shader hot cache work, man. It's badass. It's badass.
Yeah, Rourke has been talking about that for a while, actually. He's been asking us for similar features.
Yeah, it's sick. I was actually wanted to ask a little bit more of a generic question on the shader variant, and also specifically keyword issue. In doing like pre-warming work or compilation work, one of the issues I think we run in most with Vulkan is compiling identical keywords, like sort of weirdly. Like sometimes Vulkan will just decide that it, either with a shader variant or even just sometimes if you have like strict variant matching, you'll already have pre-warmed like a set of keywords, and then you'll see in the profiler that it just did it again.
Yeah.
Have you seen that behavior potentially improve with like the throwing in the cache file in the manifest ahead of time, and like is enabling and disabling things like strict variant matching something that you feel like improves that in the long run?
Yeah, thanks, Rourke. This is a good question. And I think what I'll basically paraphrase for the audience is that it sounds like you're saying, so pipeline state in graphics APIs like Vulkan, it's a very like multi-dimensional calculation. There's a lot of inputs and outputs. It doesn't just go from like shader program like SPIRV or HLSL. It doesn't just go from that to assembly. It depends on your vertex state. It depends on the meshes you're using. It depends on all these things. So I think that might be what you're seeing there. That even if you thought, and even if Unity thought that you had already pre-warmed like a certain material, certain pipeline state object, at Vulkan compilation time, it realized, wait, we actually haven't compiled this one because something about it was ever so slightly different. Maybe the vertex format was a little bit different. What I would say is that the part of why we're landing this crowdsourcing approach, like this automatic upload, is that it doesn't really matter if that's happening behind the scenes, because what would happen there is that sure, maybe you didn't do pre-warming in a perfect way because Unity was preventing you from doing that, but then you like our system is just gonna allow you to benefit automatically because we'll upload the new data to the backend.
Yeah, it's badass. No, it's really, really cool. No, so I'm excited. Hopefully, to get my hands on it.
Yeah.
All right, appreciate it, guys.
Thank you. And seems like since I went over time in the actual talk, I think that's it for the questions. But overall, thanks everyone for your time. The ball's in your court because a lot of these things, they're only perf wins if you actually grab the right version of Unity or grab the latest version of our MetaX, our core SDK, et cetera, and start benefiting. So thank you, everyone. And we can definitely form a queue and keep the questions coming if we need to. Thank you.